Hello. Okay. So, hello everyone. We are going to revise the concept of testing of hypothesis. This is the key concept of statistical inference. One of the key concepts, another is estimation. And this is the fundamental idea where people usually take the decision. So this is the decision-making tool of statistical inference. So let us first define the terminologies and the ideas. We will see some examples at the same time. So the testing of hypothesis, you can understand that it involves two terms. One is testing and another is the hypothesis. So when we say testing here, we mean the statistical testing. And hypothesis stands for a statement or conjecture about the inference of a parametric family. So whenever we have a population, we try to model it with some function. That means that a class of PDF or CDF will be describing that distribution. So that distribution can be also when the family of the distribution is fixed. That means, say for example, if you have a population and say it is normally distributed, then mu and sigma square, these are the parameters which are characterizing that family of distribution. That means if you change the value of mu and sigma square, it will change the PDF as well as the CDF, and it can cover the all possible PDFs and CDFs of normal distribution. So now, if we make a statement about the population in terms of its parameter, then that thing is usually known as the hypothesis. It is not only that you can make a general comment or statement, it should be mathematically acceptable, about the population. That is also a hypothesis here, but they can be dealt with either parametric structure or non-parametric structure. Here we are typically discussing about the parametric inference, so we will be sticking to parametric inference itself. So now we define two more terminology like null hypothesis. Null hypothesis is usually denoted by H0, and it specifies a subset of the entire parameter space. So parameter space is the all possible parameters which are admissible for a given distribution. So if the hypothesis what you are interested to test, it is making a partition in the sample space, then usually we call it a null hypothesis. And null hypothesis will be also of two categories. One is simple null. When the null hypothesis is specifying a singleton set, then it is a simple null. But when it is specifying a set which is not a singleton set, then it is known as the composite null. And the hypothesis which is standing against the null hypothesis is known as the alternative hypothesis. More precisely, alternative hypothesis will specify a subset of the parameter space which is disjoint from the set specified by the null hypothesis. It need not be the complement. So this is the fact. So I'm trying to write it down because there are many statements. So first of all, we are trying to infer about a population. So we are interested to infer about some variables, typically random variables of a population. Maybe say longevity of Indian population, height of Indian population, daily food consumption of Indian population, average weight of Indian athletes. So all these kind of things are the variables of a population. Now that the the random variable related to population is specified by its distribution. So the random variables of a population is specified by its distribution. And when we are talking about its distribution, so distribution is uniquely identified by a distribution is uniquely identified by its CDF or PDF or PMF, depending on discrete or continuous. If it is continuous, then by PDF, if it is discrete, by PMF. Okay. Now, this CDF or PDF or PMF can be regulated with parameters. And we are usually inferring about the parameters and usually doing the testing related to the parameters. But not only that, we can directly go for the testing of CDF or testing of PDF or PDF. That can be done. But in this course, or we will strictly restrict ourselves to the parameters. So here, collection of all parameters for a particular distribution, which are admissible parameters, is known as parameter space. Usually denoted by script theta. This is usually denoted by script theta. Like this, script theta. And a null hypothesis is a specification about the parameter. So example, so if you consider all normal distributions, that means all normal distributions such that mu belongs to R and sigma square is greater than 0. That means the parameter space is script theta is R cross R plus. This is positive, this is negative. So this is how it, and this contains all possible normal distributions. Similarly, you can go for binomial, beta, gamma, all this stuff. Now, we can define null hypothesis. As we have already told, null hypothesis specifies a subset in the parameter space. Okay. Null hypothesis usually denoted by H naught specifies a subset in let us call it. So this in the parameter. So this is a subset in the parameter space. So if this is your parameter space, then maybe this entire parameter space is this. Okay. Now, if the cardinality is 1, then H naught is called a simple number. And if cardinality of 10, H naught is called a composite number. Now, following the same example, if we write in this way that if H naught is same, under the assumption X follows, so assuming X is following normal mu sigma square, if H naught is claiming mu equals to 1, then it is a composite number. Because as H naught is specifying the subset which is 1 cross R plus. Okay. But assuming X is following normal mu say 1, H naught is claiming mu equals to say 1 again, because no problem with it. Then it is a simple one. Because as H naught is specifying as the set, I should write, it is a set, so 1, 1, and it is a which is a subset of this. So this quantity is a singleton set, and as a consequence it is a simple. Now, whenever there is a hypothesis, null hypothesis, there is an alternative hypothesis. That means if we don't go by the null hypothesis, we will go by the alternative. It is not like that. If the null hypothesis is not acceptable, then we are nowhere. That is not the situation. Given the data, if we cannot follow the null hypothesis, we have to go by the alternative, and we will not accept the null hypothesis in favor of the alternative. That is the motto of the work. So let me say in this way that alternative hypothesis is a subset of the parameter space itself, subset of it, let us, which is denoted by either theta 1 or theta A, satisfying so later we are calling it theta A, which is a subset of theta, and theta A intersection theta naught is agnostic. It need not be theta A union theta naught equals to, that need not be true always. It can be, but not necessarily. So this is the basic structure of hypothesis. And usually what we do, we either reject the null hypothesis with statistical test. So with a statistical test, either we don't reject the null hypothesis, or we reject the null hypothesis in favor of H1. So we reject the null hypothesis H0 in favor of H1. So if this is rejected, then we go by the H1. So how we will reject, we will see. Okay, so this is the null and alternative. But here you try to see this thing that either the null is true or the alternative is true. So when null is true, you may reject the null hypothesis, you may not reject the null hypothesis. When alternative is true, then also you may reject the null hypothesis, you may not reject the null hypothesis. So there is a 2 cross 2 situation. Okay. So First of all, let us talk about the test rule. A test rule is a statistical procedure based on the distribution of the test statistic, which will reject the null hypothesis in favor of the alternative. So, test rule will tell us whether we will reject the null hypothesis or we will not reject the null hypothesis. That we have to construct. We will see how to construct. Now, rejection region or critical region. The rejection region or critical region is a subset of Rn, which is a sample partition in a sample space, such that if we say that X belongs to the critical region is equivalent to the test statistic Tx, will reject the null hypothesis. So, if T is the test statistic for a given hypothesis, then Tx will reject the null hypothesis is equivalent to saying X is belong to a critical region. So critical region is a partition in the sample space, and typically that is if you have n samples, then that is a partition in the Rn. Okay. So if data belongs to that partition, you reject the null hypothesis, otherwise you don't reject the null hypothesis. So now let us try to see another interesting thing that I was saying here, that if we have this kind of situation that you have a null hypothesis and you have an alternative hypothesis, then what can happen when the null hypothesis is true and you fail to reject the null hypothesis? That means you are having a correct decision. So, null hypothesis is true and you are going by the null hypothesis. That means you are having a correct decision. And again, if null hypothesis is false and you reject the null hypothesis, then you are also rejecting null hypothesis is false and you are rejecting the null hypothesis, then you are also having a correct decision. But there are other two possible correct decisions, but two possible errors. One is when null hypothesis is true and you are rejecting the null hypothesis. This is known as type 1 error. And when the null hypothesis is false, but you are failing to reject the null hypothesis, then you are having a type 2 error. So why it is type 1 and why it is type 2? There is a similarity to the judiciary system. It says that, or it is a custom there, that if someone is innocent, then giving punishment to an innocent person is more severe damage to the society than leaving a criminal out. So if somebody is not innocent and you are letting that guy go, that is not so harmful under the judiciary system. So that means if the null hypothesis is false and you are failing to reject the null hypothesis, that is not so severe. So it is a type 2 error. But if null hypothesis is true and you are rejecting the null hypothesis, that is a severe error. So that is known as the type 1 error. So type 1 error is considered to be more severe error, and the probability of occurrence of type 1 error when the null hypothesis is true is usually denoted by alpha, and it is known as the level of size. We will come to that depending on the property of the null hypothesis, whether it is simple null or composite null. But the probability of rejecting the null hypothesis when it is true is usually denoted by alpha. And interesting fact is that the probability of this type 1 error and type 2 error, these two things cannot be minimized together when your sample size is fixed. That can be proved, we are not going for that. So when the sample size is fixed, if you want to reduce the alpha, then the probability of type 2 error, beta, will increase. But if you want to reduce the probability of type 2 error, the type 1 error will increase. Now, as we have told that the type 1 error is severe, so first we fix the type 1 error, the probability of the type 1 error with a cap. So we will not allow the type 1 error to be more than, say, 0.01 or 0.05 or 0.04 or 0.1. So that number is fixed. Then we try to reduce the type 2 error, and 1 minus the probability of type 2 error is known as the power. So as you have seen in estimation part, like bias or MEC are a good criteria for having a better estimator. In testing, if two tests have same level, that means or size, of probability of rejecting null hypothesis when it is true, that when the alpha is same for two tests, then if one test has better power than the other test, then which one has better power is always preferred, and it is known as the more powerful test compared to the other. So let us go by the formal definitions. That level alpha test. Alpha is a number between 0 and 1. A test is said to be level alpha test if the supremum of x belongs to the critical region. That means the null hypothesis will be rejected under H naught when theta belongs to theta naught is less than equals to alpha. Then it is known as the level alpha test. And when the supremum attains the level, then it is called the size alpha test. Notice one thing, that when theta naught is a singleton set, then level and size are same. Most of the cases in your course you will see that theta is singleton and you will be having level and size as same. And the power function is claiming that when theta belongs to the power function, you can draw for any value of theta belongs to script theta. Probability of rejecting the null hypothesis at any time you go for it, it is power. If it enters in the region for the parameter space of null hypothesis, you can restrict it for the level. In general, that is the power. So, more than one test with the same level can be compared in terms of the power function, and the test procedure with more power than other of same level is considered to be the better. That is what I was trying to say. And type 1 error is x belongs to the critical region when theta belongs to theta naught, and type 2 error, x belongs to the complement of critical region. That means you are not rejecting the null hypothesis when theta belongs to the alternative, and this is the power is known as the 1 minus of probability of type 2. 1 minus beta is the power. Okay, so here you have. Okay, so here let us just a pictorial interpretation. Suppose you are testing a null hypothesis that mu equals to 1. This one maybe so. this one. Maybe this one. This simple. So H naught mu equals to 1 versus H1 mu not equals to 1. X follows. So xi follows IID normal mu 1. Variance for the simplicity. So in this situation, suppose you are willing to test, then your critical region or type 1 error when null hypothesis is true, then your critical region might be in this red region. So if your data are falling in this red region, you can reject the null hypothesis. That is possible, and that is possible with positive probability. Similarly, another say high risk of type 2 error. So maybe say alternative is saying that maybe here your hypothesis is another case, H naught mu equals to say 0 versus H1 mu equals to 0.25. Xi is IID mu 1. Something like that. So here there is a high risk of type 2 error. So the alternative density is very close to the null density, or alternative distribution is very close to the null distribution. So there is a very high risk of type 2 error. So, but if the alternative is a little bit far away, so you can consider that this center is maybe H naught is claiming like this. H naught is claiming mu equals to 0 versus H1 is claiming mu equals to 3.7. Xi is IID. So in that situation, there is a low risk of type 2. And for the first example that we have told, either maybe it is 1 or 0, whatever way you can think of, you can go for 0 because that diagram will match with it. 0 or not equals to 0, so you can go by that. So as it will match with the diagram, center part is 0. So for that distribution, if you plot the power curve, that means probability of rejecting the null hypothesis when it is not true, then you will get a power curve which is almost expanded U type of set, and the height here at 0, that height will be the level alpha. Alpha you can consider either 0.05, 0.01 or 0.1. Okay, so this is the story for all the theoretical terms. Now, I'm not going for the construction of this or proof of Neyman-Pearson lemma, but Neyman and Pearson, they have given the first construction of a statistical hypothesis for simple null against simple alternative. So they are saying that H naught theta equals to theta 1 versus H1 theta equals to theta 1. We reject H naught in favor of H1 at level of size alpha because it is singleton, so level and size are same. If this likelihood ratio f of x theta, x given theta naught divided by f of x given theta 1 for the given data set theta less than some quantity xi such that this ratio will be less than xi with probability alpha. So satisfying this condition, the second part of the condition under H naught, because under H naught theta naught is given, theta naught you know. So under theta naught and theta 1 also known. If you construct this likelihood ratio and under theta naught if you calculate the probability, and if that probability is said to be equal to alpha, then solving this equation you can get the value of psi. And now that will lead you to the test true. So from data you can compute this thing, it will be a numeric value, and you have to compare that numeric value with the xi which is obtained from this equation. Now if this value is less than xi, you reject the null hypothesis, otherwise you don't reject the null. So that is the construction of Neyman Pearson, the most powerful test by Neyman and Pearson. But we always may not go by this one because there are other tests, and the limitation of this construction is that it is only useful for simple null against simple alternative. In real life situation, you always did not get that kind of situation. You can have composite null, you can have composite alternative. The example that you have seen, most of the cases they are composite alternative. So we can have other kind of test which is very commonly used is the likelihood ratio test, LRT, and that has a very nice properties. For that, it is recommendable that you go for a course called Statistical Inference, thoroughly studied in that. For our purpose, we will give a recipe how to perform a test, and we will show some examples, and in your course of regression you will see how to implement it. So this set of rules will be useful. So first of all, you have to estimate the parameters for which you have to do the testing. So say for example, we can write it down one way. Okay, so let me just tell you, and then we will show you. That estimate the parameters which is for which you have to do the testing. Now, after doing that, you may also have some unknown parameters, but for which you are not doing the testing. So then also you have to estimate those parameters. If there is so, you have to estimate. If there is no such unknown parameters, you can skip step. Then construct the test statistic and obtain its value. So given the data, you can obtain its value. Now, you have to, and theoretically, the test statistic is so constructed that it doesn't depend on its distribution doesn't depend on the parameter. It becomes parameter free. That is called pivoting. So getting the pivot is the challenging thing. In more general situation, that is the most challenging thing. So construction, after that, you getting the exact value of the test statistic from the given data. Then you need to know what is the exact or asymptotic distribution of that test statistic under null hypothesis H naught. Okay. So that means the pivot distribution. So under H naught, what will be the distribution of the null hypothesis? To know this thing, people have studied many sampling distributions. whatever is taught in your probability course or sampling distributions are typically helpful for obtaining this exact distribution or the asymptotic distribution of the test statistic under test. Okay. Now, depending on the alternative hypothesis and the level alpha, that means at what level you are doing the test, you have to find out the cutoff value. That means below this I will reject, above this I will accept, or below this I will don't reject, above this I will reject. So this kind of yes no rule you have to decide based on the alpha and the given alternative hypothesis. So remember, these two things are important. You need to know the value of alpha or pre-decided definitely, and the what is the alternative is saying. So rejection is always in favor of the alternative. So you must take into account what is the alternative hypothesis is. Then compare the observed value of the test statistics obtained from step 4 and the cutoff value obtained from step 5. And then conclude for the test. Or you may use the p-value. P-value, just now I am not going to describe. Maybe in the class when we will all will be present, we will describe the p-value. So this is the thing. And now let me give you an example where all these steps can be followed and we can conclude about the test. Okay, so I will come to this one, but before that, just let me show you. This is another summarization of testing of hypothesis procedure. Here is one example. When the machine produces of these reflex in set of values that average of 25. The distribution of the average produced from the machine in normal. However, suppose the supervisor is worried about the machine is out of adjustment and the producing values that you do not get average 25 pounds. So the test is in concern the random selection of 20 such observations, and the 20 observations you can see they are here, and you are testing that the sample mean is 25 pound or not. So this is the problem. So for that, what you need to do? First, sample mean estimated by population. So first you need to estimate the parameter. So let me see that in this problem, in this slide, in this problem, so H naught mu equals to 25 versus mu not equals to 25. H1. This is the problem. So step 1, you have to calculate mu hat by x bar, which is what you have obtained as 25.51. Okay. Now there, and your assumption is xi are following normal mu sigma square are IID, I running from 1 to 20. Sorry, they are IID and I running from 1 to 20. So now in step 1, you know that x bar is this. Now second step is step 2. You have to calculate the unknown parameter, which is sigma here, and that is estimated by S, and that is found to be, so this is sigma hat, which is S, which is typically 1 by n minus 1 sum over xi minus x bar whole square I running from 1. that is also found to be 2.193. N is there. Now what you need to do, you need to construct the test statistic. Okay. So to have the test statistic, so that was our third step. Construct the test statistic and obtain its value. Okay. So let us construct the test statistic and obtain its value. So consider the test statistic. Here it will be a t statistic and its obtained value is 3, step 3, t equals to 10 x bar minus mu under h naught. So let us call mu naught divided by s, and that thing is found to be 1.04. So observed. That is observed. Now what you need to do? The exact or asymptotic distribution of the test statistic under H naught. So what is the distribution of this expression under H naught? It is following T distribution with 19 degrees of freedom, n minus 1 degrees of freedom. So is 4. T is following T distribution with 19 degrees of freedom under H naught. Under H naught it is following now what you need to do? You need to know the cutoff value given the null distribution as well as the level of the test. So that is your next step. So step 5, let's go ahead. So here you can see that the cutoff values are given here, that 2.093. So they are the cutoff value for 19 degrees of freedom, and alpha is 0.05. So if you choose step 5, alpha equals to 0.05, then tau alpha by 2 at degrees of freedom 90 is how much? They have given 2.093. Now you will reject the null hypothesis if the observed value is either larger than 2.093 or less than minus 2.093, because T distribution is symmetric around 0. But you can see that the observed T value is 1.04, which is less than 0.293. So what is your conclusion of the comparison is this, in this way, that step 6, that T observed, which is this one, equal to 1.04, which is strictly less than tau alpha by 2 90, or more precisely, if it is negative value, then also you need to take the mod, and this is so, and hence we give, this is the statement, given the data, we cannot reject H naught in favor of H at level alpha equals to 0. This is the correct statement to give after any testing procedure. Either we write we cannot reject the H0 or we reject the H0 at level this. So this is the right way to write down after any testing conclusion. So this is all about what we do in a particular testing problem. So this is a very simple and nice example that we have seen. Now let me minimize this thing and let's talk about a little bit more. Okay, so here is a simulation that you are drawing 10 samples from normal 10.5 and 1.2 standard deviation, 10.5 mean. Then the unbiased estimator of the mean is this, sample mean, sample variance is this, alpha you set, then you are testing mu equals to 10%, mu not equals to 10, when sigma square is known, then you have to do the Z test. If you don't dividing it by estimated sigma, it will be a standard normal. And here you can see the computer given the observed value of the test statistic is this, sample size is this, standard deviation is set, sample mean is this, p-value we will discuss later, but based on p-value you can say that whether you are rejecting or not rejecting. So p-value is typically telling us the probability of the rejection probability above or depending on the situation greater than, less than, or both sides. We will talk about it later on. So if your p-value, typically the rule, if your p-value is less than alpha, you reject the null hypothesis. If your p-value is larger than alpha, don't reject the null hypothesis. That is the rule. But how to compute the p-value, that is important, because many cases the computer may not be able to calculate the p-value, but any package of the software, they are supposed to provide the p-value. Okay, maybe truly or approximately. So given these p-value, we don't reject the null hypothesis. Okay, similarly, when sigma square is unknown, then also you can see that p-value is quite high, and you can get a t-distribution with 9 degrees of freedom because you have 10 data points, 10 minus 1, 9 degrees of freedom. And you can see both of the cases sample mean are unchanged, and confidence interval we will talk about distance. And here is another example, which is the third one. Sigma square equals to sigma naught square versus sigma square not equal to sigma naught square when mu is unknown. So that is talking about the variance. Not only you have to test for mean, you can do testing for variance also. So it will give you a chi-square test, because you know that xi minus x bar whole square divided by sigma square is following chi-square distribution. So from there you can construct a chi-square test. And again, here the p-value is less than 0.05, so you can reject the null hypothesis in favor of the alternative hypothesis at level alpha. Alpha is 0.05. The estimated variance is 2.72, whereas the true variance is, I think I have written here, unbiased estimate. So that will be 1.2 whole square, 1.4. Okay, so these are the things you can go for your exercise, that x1, x2, xn are IID normal mu sigma square, and y1, y2, ym are IID normal mu 2 sigma square. Remember, mu1, mu2 need not be same. Your null hypothesis is claiming mu1 equals to mu2, alternative is claiming mu1 not equals to mu2, but sigma square are same. So in that situation, you can have a pooled estimate of sigma square. So that pooled estimate of sigma square can be obtained from both of the samples. So let me just tell you how you can do it. So here, so exercise 163, that x1, x2, x1, x2, xn IID normal mu1 sigma square, y1, y2, yn normal mu2 sigma square, IID, and they are also independent. But your H0 is claiming mu1 equals to mu2 and H1 is claiming mu1 not equals to mu2. Now sigma square common, sigma square unknown. So in that case, the common estimate of sigma square can be obtained in this way, that sum over xi minus x bar whole square I running from 1 to n plus sum over yi minus y bar whole square I running from 1 to n whole divided by n plus n minus 2. This will be the estimate of sigma square. And why this will be? Because we define x bar as 1 upon m sum over xi and y bar equal to 1 by n sum over yi. So this quantity sum over xi minus x bar whole square I running from 1 to n divided by sigma square is following chi-square in minus 1 degrees of freedom. At the same time, yi minus y bar whole square divided by sigma square is following chi-square in minus 1 degrees of freedom, I running from 1 to n. So this quantity sum over xi minus x bar whole square plus sum over yi minus y bar whole square whole divided by sigma square is following chi-square in plus n minus 2 degrees of freedom. Okay, so now we can, now if you take the expectation, you will be getting, so this is chi-square n plus n minus 2. So if you take the expectation, so that means if you take the expectation, sum over xi minus x bar whole square plus sum over yi minus y bar whole square 1 to n divided by n plus n minus 2. This quantity is sigma square times n plus n minus 2 divided by n plus n minus 2, and that is how this is a legitimate, and not only that, an unbiased estimator. So your test statistic will be x bar minus y bar whole divided by sigma hat square, we check this one, and this will follow t distribution with m plus n minus 2 degrees of freedom under h naught, and you will have a both tail test. Either here you reject or here you reject. So absolute value of t observed, if it is greater than tau alpha by 2, so this region is alpha by 2, this region is also alpha by 2, this point is tau alpha by 2, n plus n minus 2. If this thing holds, reject h0 in favor of h1. So that is the way to do this test. Similarly, perform a test for mu x equals to mu y when you have a data from bivariate normal distribution. It is known as a paired t-test. There is also an interesting test for so let me also give you the hint. So this is for exercise 163. So for paired t-test, what you have to do, you have xy yi paired observation, xi yi paired observation, I running from 1 to n. You define di equals to say xi minus yi for I equals to 1 to up to n, and so di will follow normal distribution with mean 0. So expectation of di equals to 0 under h0, and variance of di equals to say sigma square t that value is known. So now it is a known test for you. Given the data, you know all the values of di. You know how to do testing mean equals to 0 sigma square r. So it is a very trivial problem. This is known as the paired t-test, and that is for exercise 164. Paired t-test. And finally, proportion test. Hardly we will require for this regression course. I am leaving this one as an exercise. And equality of variance test. Already you have seen how you can estimate two variances. So this will be an example of F test. 166. So from these two things, already you know that sum over xi minus x bar whole square I running from 1 to n. This is following, but divided by sigma square is following chi square n minus 1 degrees of freedom, and yi minus y bar whole square I running from 1 to m divided by sigma square is following chi square m minus 1 degrees of freedom. Already you have seen, and they are independent. So if you consider a statistic xi minus x bar whole square I running from 1 to n divided by n minus 1, and yi minus y bar whole square I running from 1 to n divided by n minus 1 whole square. This is supposed to follow f n minus 1 n minus 1 under h naught, and you will have an upper tail test. What is the alternative? Okay, so you will not have a upper tail test, you will have a both tail test. So less value and high value. So, and it is, as it is not symmetric, you have to reject the null hypothesis. So this region is alpha by 2. So this is f alpha by 2, and this region is alpha by 2. So this is f1 minus alpha by 2 with the same degrees of freedom, n minus 1, n minus 1, n minus 1, n minus 1. So if the data f observed falls here or here, you have to reject the null. So all these things you can do by yourself, practice it. You will have a very nice chart of all these kind of test statistics, their rejection rules, right side, left side, both side. In this Wikipedia page, this page is very nice. And also you can read these books. I think I'm done enough. If you have any query, we will have any doubt. Okay, thank you.